In this lesson, we're going to be looking at identifying dilations. We're going to focus on identifying a dilation of a 2D or 3D object and using similarity to determine and explain dilations. The outcomes we're going to cover are: determine and explain whether a given image is a dilation of another given shape using the concept of similarity. Identify and describe the applications of transformations in construction, industrial, commercial, domestic, and artistic contexts. And solve a contextual problem that involves transformations. So to start, what exactly is a transformation? Well, a transformation is a change in a figure that results in a new position or size. So moving an object around or making it get bigger or smaller. So some examples, and we're going to cover all of these in this unit, are dilations, translations, reflections, and rotations. There are other types of transformations, but these are the ones that we're going to focus on. Next, we have the image. When we have a transformation, we have a new image that is created. It's the final shape and or position of a figure after a transformation. So depending on the type of transformation, we could have a new shape, a new size, or we can have it, our image in a new location. What we're going to focus on in this particular unit, in this section, is a dilation. And a dilation is a transformation in which a figure is enlarged or reduced by a constant factor. You can see the happy face here on the page in the top right corner. The little one would be considered an object, and the bigger one is an enlargement, which is what we refer to as the image. It's the transformation. And if a transformation is a dilation, this is kind of important, the object and image are similar. Similar objects mean that the ratio of their corresponding sides are equal and the corresponding angles are equal. So they're proportional to one another. And when we're doing a dilation, we're multiplying by some constant factor. That constant factor we refer to as a scale factor. And it's a factor or a number by which all dimensions in a two-dimensional object, that would be the length and the width, or the base and the height, which all dimensions of an object are enlarged or reduced. So an example would be, you can see the two rectangles on the right. The dimensions of this smaller rectangle, which are 2 by 1 right now, are multiplied by 3 to give us a 6 by 3 rectangle. So the length is multiplied by 3, we go from 2 to 6, and the width is multiplied by 3, we go from 1 to 3. So the scale factor in this dilation is 3. So when an object is dilated, that means when it's enlarged or reduced, each dimension is multiplied by the scale factor. So what happens to the area of an image when both of your dimensions are multiplied by the scale factor? Well, let's look at that dilation that we had on the last page. We started with a rectangle that was 2 by 1, and we multiplied it by a scale factor of 3. So now our image is 6 by 3. The area of the original object is the length times width because it is a rectangle. The length is 2 and the width is 1, so we multiply 2 by 1, and that gives us a total area for the smaller rectangle of 2. For the image, it's still a rectangle, so we still follow the same formula. The area of the image is going to be length times width, but I have a new length and a new width. 6 times 3. My new length is 6, and my new width is 3. So multiply 6 by 3, and I get 18. So what you'll notice is that my area is much more than 3 times larger than the area of the object. So now we're going to compare these areas and see what kind of a relationship we can uncover. Dividing the area of the image by the area of the object So the image, remember, had an area of 18. The object had an area of 2. So we divide 18 by 2, and that gives us a value of 9. So my area of my new image is 9 times larger than the area of the original object, is what that's telling me. The ratio of the areas is 9, but remember, our scale factor was only 3. So how can I relate the number 9 to the number 3? Well, 9 is equal to 3 times 3. Or in other words, it's equal to 3 squared. And when dilating, the area of the image is the object's area, whatever the area of the original object was, multiplied by the square of the scale factor. So in this case, our scale factor was 3, and the area increased by a value of 9. We multiplied both the length and the width by the scale factor of 3. So both my length and my width are 3 times larger than they were before. If the length and the width are both 3 times larger than they were before, the area is the length times the width. So we have 3 times the length times 3 times the width, and that'll give us 9 times the original object's area. So that is true for all dilations. If it's a true dilation, your length and your width, or whatever dimensions you have, are going to be both increased by the same factor, which means that our area is going to be equal to the scale factor squared times larger than the original object. We're going to look at this example now. This is identifying a dilation, determining whether or not what we have here is a dilation. Tyler wants to insert this image on his blog. It has to fit into rectangle EFGH. Will the image fit if he reduces its size proportionally? So if we have a dilation, if we have a reduction that's a dilation, you're going to have all of your corresponding angles equal to each other, as well as the ratio of the corresponding sides. So what I'm going to do first is I'm going to measure the angles on all 8 of my angles that are present here. Angle A, B, C, and D in the first rectangle, and angles E, F, G, and H in the second rectangle. Now we're told it's a rectangle, so it might be okay to assume that we have 90-degree angles, but it's always a good idea to check. So I have a protractor here, and you can see it's placed on angle D right now, and it gives us a value of 90 degrees. I'm not going to bore you by showing myself rotating my protractor to get all those angles, but you're more than welcome to do that yourself, and you'll find that all of your angles should be equal to 90 degrees. So if we're going to compare those corresponding angles in the object and the image, angle A was equal to 90 degrees, and the corresponding angle is angle E, and that's also 90 degrees. Angle B is 90 degrees, and the corresponding angle in the smaller rectangle is angle F, and that's also 90 degrees. Angle C is 90 degrees, and the corresponding angle is angle G, which is also 90 degrees. And finally, angle D is 90 degrees, and the corresponding angle on the image is angle H, which, again, is also 90 degrees. Now we're going to look at measuring our side ratios. So in order to do that, you have to measure both the length and the width of your image and your object. Here you can see I've measured one length and one width of my object. If you do that for all the sides in your object and your image, you're going to find that side AB is equal to 10. You're going to find that BC is equal to 5. You're going to see that CD is equal to 10, and DA is equal to 5 as well. Again, I'm not going to bore you by showing how I measured all 8 of these sides, but I'll give you the values that I calculated. For side EF on my image, I calculated a value of 5, or I measured a value of 5. For side FG in my image, I got the value of 2.5. For GH in my image, I got a value of 5. And last but not least, for side HE, I measured a value of 2.5 again. So now we're going to perform ratio calculations on our corresponding sides. So AB corresponds from the object to EF on the image. And the value of the ratio is 10/5, which is 2. For side BC, it corresponds to side FG in the image, and the measures are 5 divided by 2.5, which also works out to 2. Side CD corresponds to side GH in the image, and the ratio of the two sides is 10 divided by 5, which is 2. And lastly, side DA corresponds to side HE, and the ratio of those two sides is equal to 2 as well. So what we see now is that all of our side ratios are equal. They're all equal to 2. So we know that the corresponding angles are the same. They're all 90-degree angles. We know that the side ratios are the same, so the sides must be proportional. When the ratios are the same, the term we use is proportional. The image is similar to the rectangle, the original object. And if he reduces the rectangle, the object, the image will fit. So seeing as how the images are similar due to the fact that the angles and the side ratios are the same, that means that this image is a dilation. So to summarize what we've talked about in this lesson, a transformation is any change to an object. It could be a dilation, it could be a translation, it could be a reflection, it could be a rotation, or it could be some combination of those different potential transformations. You can have a dilation followed by a translation, or a translation and a reflection with a rotation. You can have any plethora of different transformations. Whenever you have a transformation on an object, however, the new object is called the image of the original object. A dilation is either an enlargement or a reduction of an object by some scale factor. So your dimensions in your object are all going to be multiplied by the same scale factor to get either an enlargement or a reduction. The scale factor must be applied to all dimensions. So we can't get a dilation if we only multiply, say, the length of a rectangle by some scale factor, and we neglect to do it for the width. We're actually creating a completely different type of object in that case. And dilations have the same corresponding angles and corresponding side ratios. In other words, dilations are similar objects.